Snaith, who again is from Bristol. She is from the Department of Mathematics. She is a reader in mathematics and belongs to the quantum chaos group, and she also is an EPSRC Advanced Research Fellow.
So I work on random matrices and number theory, and it's sort of an odd combination of subjects because random matrix theory is a subject that was actually developed by nuclear physicists around the 1950s, and number theory is obviously an area of pure mathematics, and so it's sort of a bit of a funny mix of subjects, but that's in fact what makes it a really exciting topic, which is hopefully what I'll tell you about today. So actually the means by which I got here is a similar sort of patchwork of random happenings. So I grew up in Canada, and I knew I wanted to study science at university, and in Canada you go to university and you study a year of general science before you decide which subject you want to specialize in. And so at the end of my first year I thought, well, maybe biology, maybe physics, maybe mathematics, and actually I decided I didn't want to be a mathematician because my father's a mathematician, and I can remember at the age of about 6, after several summer holidays which had been at mathematics conferences around the world, vowing to myself, what I am not going to be is a mathematician. And so in my second year of university, trying to decide what subject to do, I said, well, it's not going to be mathematics. So I studied physics, and during the summers I worked as an intern for a professor of physics, and he worked in quantum chaos, which is an area of physics. It's sort of trying to explain what is chaos in a quantum regime where you don't have exponentially diverging trajectories. But it's an area of physics which uses random matrices. And so I really liked this, and I decided I wanted to do a PhD in some related area. And so I talked to the professor I was working with for some suggestions of where I could do a PhD, and he suggested various places. And they were mainly in Europe, and I was in Canada, so I couldn't visit these places. So it was a matter of emailing the professors and saying, can I work with you? And then just sort of a random choice of who wrote the nicest email. So John Keating from Bristol wrote me a very encouraging email. So I thought, okay, so I'll go to Bristol to work with John. And it was just sort of by luck that I arrived in Bristol at exactly the right time, because, as I will tell you, it's been known since the 70s that there's a connection between random matrices and the Riemann zeta function and other number theoretical functions. But it was in 1996 when I arrived in Bristol that the number theorists sort of said, okay, it's time that we actually get something concrete out of this. Physicists had been working and making sort of analogies for a while, but the number theorists said, can you physicists really make some predictions that will give us some concrete suggestions or conjectures about something in number theory, and I landed in Bristol at exactly the right time to become part of this project, and so I got to sort of help in the development of this whole field, which has been really exciting. So hopefully I can convince you today of how exciting this connection between physics and number theory is. So the connection sort of starts out with the Riemann zeta function. So the Riemann zeta function is a very important function in number theory. So one of the ways to write it is this product over primes. Humankind have been studying prime numbers for over 2,000 years, and you'd think by this time that we'd know everything there was to know about them, but that isn't the case. There is still lots of mysteries about how the primes are distributed amongst the integers that mathematicians don't understand. And so obviously you want to be able to use every tool you can to study the prime numbers. And so here by sort of encoding them in a function, you can use analytic methods to study prime numbers. So that's why the zeta function is important to number theorists, because you can use it to study the primes. So you can write it as this Euler product over primes, or as a Dirichlet series over integers. And these two expressions are equivalent, and they converge when the real part of S is greater than 1. So in this blue region here. But you can do an analytic continuation so that you have a function on the whole of the complex plane. And then the interesting points are, well, so it has a pole at 1. It has zeros on the negative real axis, which are well understood. They occur at the negative even integers. And then the Riemann zeta function has an infinite number of complex zeros which lie somewhere in this strip here where the real part of S lies between 0 and 1. And of course, the famous Riemann hypothesis says that in fact all these zeros lie precisely on the line where the real part of S is equal to a half. So the Riemann hypothesis says that they lie as I've drawn them on this vertical line. So these are the zeros that we're interested in. Since we're often interested in the zeta function on this critical line, this line where the zeros supposedly lie, we often write zeta of a half plus it. So if t is real, we're just looking at the zeta function on this line where the real part of s equals a half. And if t is a real number, it measures the height at which we're considering the zeta function on this line. So in terms of random matrix theory, what we're interested in is the distribution, the positions of these complex zeros. And the first thing that you notice if you look at these zeros is that they become denser higher up on the critical line. So if I'd drawn this much further, you'd see that the red stars were getting closer and closer together as you go up. This density grows logarithmically. So the density of the zeros is 1 over 2 pi log t over 2 pi. So asymptotically, when t is large, it looks like this. But it's not actually this sort of steady increase in density that we're interested in. So often what we want to do is scale away that steadily increasing density by sort of stretching out the critical line so that we get a set of points which have, on average, just unit spacing. So just a distance 1 between consecutive zeros. So often what we do is we take the nth Riemann zero, Tn, and multiply by the density of zeros around that point, 1 over 2 pi log Tn over 2 pi, and then we get a set of points Wn, which on average have consecutive spacing of just 1. So now we have this set of points with unit average spacing, and we want to talk about their distribution. How do they fluctuate around this average unit spacing? So there's a good picture to illustrate this from Mater's book on random matrices. So here are a few selections of positions or heights, if you like. So over here we have completely random points. So this is what you get if you blindfold someone and ask them to pick random points on this interval. You might get a picture that looks something like this. So you'd have areas where no points have landed, and other places where several points have landed so close that you can't even distinguish them. That's what these little ticks mean. So this is what you get if you just put random independent points on an interval. On the other side, we have completely uniform periodic points. And in between, we have various other collections of numbers. So here is a little section of prime numbers. They look like this. These are the sort of excitation levels of some large atomic nucleus. These are the energy eigenvalues of a quantum billiard. So that's essentially if you take some small particle like an electron, you confine it to some weird shape in space, then its energy levels might be distributed something like this. That's called a quantum billiard. And here are some of the zeros of the Riemann zeta function, right? So those red stars that were on the previous slide, if you take a section of the critical line and you plot the positions of those red stars, then you get something that looks like this. And we want to ask questions about the distribution of the heights of the Riemann zeros. And so you can see, just even by looking at it just by eye, that they look a lot more like the uniform points than they do like the random points, right? I mean, they're not completely uniform, not completely periodic, but they do look a lot more like this side of the picture than like that side. So that's something we can say just looking at it by eye, and obviously we want to sort of quantify that mathematically. So there are lots of different statistics you can look at, but let's talk for a minute about the connection with random matrices. So in this context, we want to think about unitary matrices. So imagine you've got an n by n unitary matrix. Well, so a unitary matrix has eigenvalues that lie on the unit circle. So maybe they look something like these blue stars here. So we can write the eigenvalues as e to the I theta n, right, where theta n is real. So they lie on the circle. So you can imagine that's what it looks like if you pick one n by n unitary matrix. But we can think about the whole space of n by n unitary matrices. And we want to talk about random matrices, and so if you want to talk about a random matrix, then you also need some kind of measure on your space of matrices, right? So you need some way to weight, if you're doing an average, to weight to one matrix versus another. So you have this space of matrices, you want to put a measure on it. It turns out that the space of unitary n by n matrices is actually a group. It's a compact group, the group UN. And so you have a Haar measure on that group, which is a sort of natural measure. It's the measure that weights all the matrices in the space equally. So it's a kind of flat measure. So now we have a space of matrices and we have a measure on it. So now we can talk about picking a matrix at random from that group, or if you like, about averaging some quantity over that group of matrices. So for example, if you wanted to say, as you look over the group of n by n unitary matrices, what's the probability of finding, 3 eigenvalues in the interval, between 1 and some point on the unit circle, you can do that kind of calculation because you have this group with a measure on it. So that's what we mean by a random matrix, a matrix drawn at random from the set of all n by n unitary matrices with this flat Haar measure on it. So if we look at these eigenvalues, well, they're just points on a line, right? If you like, you can imagine sort of slitting the circle and opening it out so that it's a line. But basically, we have points on a line, and we want to understand their distribution in the same way as for the zeros of the Riemann zeta function. So there are n eigenvalues on the unit circle, so their density is n over 2 pi. So if we wanted to have eigenvalues that had average spacing 1 between them, we just stretch the circle by the density n over 2 pi, and then we'd have a set of points with average spacing, average consecutive spacing 1. And then we can compare the statistics of those points with the statistics of the zeros of the Riemann zeta function. So there are lots of different statistics you could pick to sort of characterize what's going on with the distribution of these points. The most famous one is the 2-point correlation function. So I'll tell you where this picture comes from. So the crosses on this picture are from the data, so from the Riemann zeros. So this is what you get if you take the first 100,000 Riemann zeros, so starting at the point 1/2 on the picture of the Riemann zeta function, you count up and you calculate 100,000 zeros. So now you have a set of data with 100,000 points, and now take every possible pair of zeros and calculate the separation distance between those zeros. Okay, so now you have a set of data which is, 100,000, choose 2 points, which are the distances between every possible pair of zeros, and then you just make a histogram of those separation distances. And what you get is this set of crosses. So the smooth curve is the random matrix result. So to do the random matrix theory, you can imagine you could take a unitary matrix, some big unitary matrix. You can calculate its eigenvalues. You can take every possible pair of eigenvalues and calculate the separation distances and plot a histogram, right? And then if you wanted so that would be the 2-point correlation function for a particular matrix. If you wanted sort of an average 2-point correlation function, you might imagine generating lots and lots of unitary matrices and sort of averaging their histogram, the histograms of spacings between the zeros, which would be a perfectly valid way to get a similar picture. But it turns out that in random matrix theory, it's often quite easy to do calculations, like analytically do a calculation, which is very hard to do in the number theory setting. So it turns out that in random matrix theory, you can actually write down a formula for the 2-point correlation function, so you don't have to generate the picture numerically. And this is the formula. In fact, this is the limiting form of the 2-point correlation function when your matrix size becomes really, really large. Right, so you can also write down a formula for any finite size matrix, but this is what you get if you let your matrix size tend to infinity and you're asking what is this 2-point correlation function, so that relates distances between pairs of zeros. So the answer is the 2-point correlation function is 1 minus sine pi x over pi x squared, and it's this solid curve on this picture here. So the solid curve is random matrix theory. The crosses are the data calculated from the Riemann zeta function. So you can see for the first 100,000 zeros, we get some sort of approximate agreement between these two pictures. If you look a little higher up on the critical line, so take zeros further from the point 1/2, so here using 10 to the 5 zeros around the 10 to the 12th, so that's quite high up on the critical line, you get the Riemann zeta data matches even more closely the random matrix theory. And if you're Andrew Odlyzko, you can calculate 79 million zeros around the 10 to the 20th zero. So this is really like amazingly high up on the critical line. And then you get absolutely beautiful agreement between the two-point correlation function of the Riemann zeros and the two-point correlation function of very large random matrices. So, so some things to note about this picture. I mean, the fact that this curve drops down to 0 at 0 means, if you think about it, it means we're very seldom finding pairs of zeros that are very close together, right? So the Riemann zeros don't like to be very close together. And you can see this curve goes quadratically at the origin, and so does the curve from random matrix theory. And this is, I mean, you wouldn't see this if you were looking just at random numbers on the line. So there's something which is very characteristic of the behavior of the Riemann zeros, and it's modeled perfectly by eigenvalues of random matrices. Right. So this picture is it's hopefully convincing you that at least if you look at zeros very high up on the critical line, their distribution is modeled very well by large random matrices. So this sort of experiment is done with the scaled Riemann zeros, so they've been stretched out so they have an average spacing of 1. And so you can see the scale goes up to 3. So at least if we're looking on scales of just a few mean level spacings, random matrix theory really does a phenomenal job of matching these statistics. So I have a few mysteries as we go along through the talk, and some of them will be explained by random matrix theory, but here, mystery 0 is actually a mystery that we don't have an answer to. So the question, why are these statistics the same, is one that no one really knows the answer to, right? So we have these random matrices on the one hand, and this very particular number theoretical function on the other, and there's no obvious reason why there should be anything that makes the one model the other particularly well. I mean, some people, tried to solve the Riemann hypothesis by finding a matrix which has eigenvalues, which are the zeros of the Riemann zeta function. So maybe there's some hidden matrix behind the Riemann zeta function, but I mean, so far, no one really has a good answer to this question of why the statistics are the same. But nonetheless, I mean, we have a convincing picture, and there are also some sort of semi-rigorous results which lead in the same direction. So we're convinced that there is a connection, and we want to use that to do some calculations. So just before I tell you about those, I guess the natural question is, like, why would anyone have ever thought to compare these two things? Because there's no obvious reason why you would want to. So there's a good story behind this. So in 1972, Hugh Montgomery was a very young number theorist, and he was studying the distribution of the Riemann zeros, and in particular this two-point correlation function statistic. So he had a formula, and so in number theory you can't quite prove that this is actually the two-point correlation function for the Riemann zeros, but he conjectured that that was true, and he had a sort of a partial proof of this result. And so in 1972, he was visiting the Institute for Advanced Studies in Princeton, and at the same time, it happened that Freeman Dyson, an eminent physicist, was also visiting the Institute. And as I understand, at the Institute, everyone gets together in the afternoon to have tea at a certain time. And someone introduced these two men. At first thought you would think that they wouldn't actually have anything, in common concerning their research. But Hugh started to tell Freeman Dyson about his research and this two-point correlation function of the Riemann zeros. And Freeman Dyson, who had studied random matrices, looked at this formula for the two-point correlation function and said, that is exactly the formula for the two-point correlation function of eigenvalues of random matrices. So it was like this complete coincidence, right, that these two happened to be introduced, which led to this whole field starting. And Hugh gave me a copy of this letter, which is rather nice. So it says, on April the 7th in 1972, Freeman Dyson wrote to Atlee Selberg. Perhaps he didn't know how to contact Montgomery, But anyway, so he wrote, Dear Attlee, the reference which Dr. Montgomery wants is, and he names the most famous book on random matrices and gives the equation showing that the pair or the 2-point correlation function of the zeros of the zeta function is identical with that of eigenvalues of a random complex matrix of large size. So this is what started off this whole field and is one of the reasons why I'm here today. So, but the point was, as I said, just before I started my PhD, so in 1996, you know, a lot was known that there was this connection between random matrices and Riemann zeros, but in 1996 there was a conference in Seattle where there were, well, it was a conference on the Riemann hypothesis, so lots of number theorists were gathered together to try and see if any progress could be made on the Riemann hypothesis. And so basically, you know, anyone who had anything to do with the subject was invited, and so some physicists were invited. And in particular, at this conference, Peter Sarnak, who's a very distinguished mathematician who works in number theory, amongst other things, sort of put out a challenge, in particular to John Keating, saying, you know, let's calculate something using random matrix theory. You know, can you go away and calculate something that's interesting to number theorists using random matrix theory? You know, because there's been this connection for a long time, but we need to see some results coming out of it. And so John Keating returned to Bristol, and he's not a man to let a challenge go unanswered. And so he decided that this was going to be what he was going to work on. And I happened to be the graduate student who was starting right then. And so I was lucky, happened to be in the right place at the right time, and got to work on this project of trying to do some actual calculations doing random matrix theory. So I'm going to tell you a little bit about what has resulted from that. So the Riemann zeta function. So let's think about the logarithm of the Riemann zeta function. So if you look at some interval high up on the critical line, so between t and 2t, and you think about the logarithm of the Riemann zeta function on the critical line. So this is a complex number, and if you imagine sort of sampling it in this interval, and if you normalize correctly, then what this theorem of Selberg says is that if your interval now goes really, really high up on the critical line, then sampling these normalized values of the log of zeta is exactly the same as sampling a complex Gaussian. So if you like, the real and imaginary parts of the log of zeta are independently Gaussian distributed. Right, so this is the theorem of Selberg's. So we know that in the limit, as you go very, very high up on the critical line, the log of the zeta function is distributed like a Gaussian. So in the 80s, Andrew Lisko, who does these amazing computations for the zeta function really high up on the critical line, he created a numerical distribution of the real part of the log of zeta high up on the critical line, and again working up around the 10 to the 20th zero. So this is phenomenally high up on the critical line. And he compared the plot to the standard Gaussian. So the Gaussian is the black curve. The numerical data for the zeta function around the 10 to the 20th zero is the red curve. And I mean, based on the theorem on the previous slide, you would really expect that the red curve would lie smack on top of the black curve. But it doesn't. So I mean, just to repeat, it's a theorem that if we went infinitely high up on the critical line, the red curve would converge to the black curve. But obviously, even though we're incredibly high up, convergence is extremely slow, and the red curve still hasn't converged to the Gaussian. And so, you know, the natural question is, you want to know how fast is the red curve converging to the black curve. You want to sort of quantify that somehow, and that couldn't really be done using the standard number theoretical techniques. So we want to try and do that, try and understand that curve using random matrix theory. So if we want to model the log of the zeta function using random matrix theory, we need some analog of the Riemann zeta function. So the Riemann zeta function is a function, obviously, that goes to zeros at the zeros of the Riemann zeta function. So the similar thing in random matrix theory is a function that goes to zero at the eigenvalues of the random matrix. So that would naturally be the characteristic polynomial. So you can write the characteristic polynomial in various ways, but I write it here as a product over the eigenvalues. Remember, the eigenvalues we e to the I theta n. So we write product over the eigenvalues, 1 minus s e to the minus I theta n, so the inverse of the eigenvalues. So that tells us if, imagine S is on a unit circle, every time it passes through an eigenvalue, this function is 0. Right, so the characteristic polynomial is going to be our analog of the Riemann zeta function. And so if we look at the distribution of the log of the characteristic polynomial, we might hope that that might tell us something about the distribution of the log of the Riemann zeta function. And we know from the pictures of the two-point correlation function that the limit as we go very, very high up the critical line corresponds to the limit of very, very large random matrices, right? So T going to infinity is like n, the matrix size going to infinity. Obviously, in order to compare with the picture that Odlyzko drew at the height 10 to the 20, we need to know at what rate n and t goes to those two equivalent limits. So we want some way to relate n and t. So the natural thing to do is to relate the density of zeros. So if you remember, the density of the zeros of the Riemann zeta function was 1 over 2 pi log t over 2 pi if we're at height t on the critical line. And the density of eigenvalues on the unit circle was n over 2 pi. So essentially, for large t, we have that n is like log t. So taking what we've just put down on this slide and making a plot here, we now look at the value distribution of the real part of the log of the characteristic polynomial and plot it versus the real part of the log of the Riemann zeta function. So Odlyzko's red data was calculated at the height of the 10 to the 20th 0, which, if you use the n is like log t analogy, corresponds to 42 by 42 unitary matrices. So the green curve here, which is almost indistinguishable from the red curve, is what you get if you look at the distribution of the real part of the log of 42 by 42, the characteristic polynomials of 42 by 42 random unitary matrices. And you can see that the agreement is really good. It's really convincing. So the random matrix theory models the number theory, but the good thing is that in random matrix theory, it's much easier to do these calculations than in number theory. And so you can actually get, essentially a formula for this curve, and you can understand exactly how it converges to the Gaussian, because clearly, as the matrix size goes to infinity, the real part of the log of the characteristic polynomial also tends to a Gaussian, as you'd expect. But you can also look at the lower order terms as it converges to this Gaussian. You can understand the rate of convergence, and from that you can make very detailed conjectures about how the data from the Riemann zeta function converges to the Gaussian too, and you understand that it's essentially a logarithmic convergence, and that's why it's so slow. Another mystery, which potentially can be solved using random matrix theory, is the question of how big does the zeta function get very high up on the critical line. So the Lindelof hypothesis is another famous hypothesis which is related to the Riemann hypothesis, and it says that the zeta function, so zeta of a half plus it, that is zeta on the critical line where its zeros lie, doesn't grow faster than t to the epsilon, where epsilon is anything greater than 0. So this gives you a bound on how fast it grows. So assuming the Riemann hypothesis, then zeta of half plus it doesn't grow faster than the exponential of some constant log t over log t. But there's also a result that says the zeta function gets at least as big as, or grows at least as fast as, the exponential of some constant root log t over log t. Right? And so there's a gap in between this, which is the maximum rate at which it can grow, and this, which is sort of the least rate at which it can grow. So the question is, what is the real answer? How fast does zeta really grow as you go high up on the critical line? And so there's a very nice formula produced by Gonek, Hughes, and Keating a few years ago, it's a beautiful result, so I've written this down, but what you really need to look at is this line here. So they write zeta as the product of a product over primes and a product over zeros. So this here is a product over primes, and essentially the x is like a balancing factor. So when x is large, you have a long product over primes and a short product over zeros, and when x is small, you have a short product over primes but lots of zeros contributing, and they have an explicit error, which I didn't write down because it looks a bit complicated. But so they have a theorem which writes the zeta function as a bit which involves primes and a bit which involves zeros. And then Farmer-Garnick and Hughes use that hybrid formula to look at maxima of the zeta function. So the point is that you use arithmetic on the prime bit of the formula, and you use random matrix theory on the bit that depends on the zeros, and you sort of assume independence and look at the maxima of the prime bit and the zero bit separately, and they came up with a conjecture for the size of zeta, which is big O of e to the constant root log t times log t. And so it's actually, looking at the data, it's actually really hard to tell which conjecture is right. But it's sort of exciting that random matrix theory can come along and possibly suggest answers to questions that have been around for such a long time, like this in number theory. So that's it's sort of that. I've given you just the very basics of this subject, but hopefully it gives you a sort of hint of the fact that you can use random matrix theory, where you can do very concrete calculations relatively easily, and conjecture answers for questions that are of interest in number theory and that are very, very hard to get a hold of using number theoretical techniques. So that's basically all I want to say, except to say that the Riemann zeta function is just one particular number theoretical function, and there are a whole load of other similar functions. So they're called L functions, and they have many of the same characteristics as the Riemann zeta function. And so, based on these results from sort of 10 or 12 years ago with the Riemann zeta function, you can go on and apply this to any different sort of L functions, and there are L functions associated with all sorts of quantities in number theory that people are interested in. So, for example, at the moment, we're interested in seeing if we can say anything about elliptic curves using random matrix theory. So an elliptic curve is an equation like y squared is some cubic in x, and there are lots of people who are very interested in, for example, counting the number of rational points that satisfy this equation. And again, it's something that's it's a very, very hard topic in number theory, and we'd like to hope that we could use random matrix theory, where calculations are easier, to answer the sort of questions that number theorists are interested in. So yes, so the past 10 years has been very exciting in this subject, and we hope that we'll go on and find even more exciting results. Thanks.
Theorem that there's an infinite number of zeros on the infinite line?
Yeah.
So the very earlier slides you showed, you had this formula 1 minus sine squared of and that was sort of the limiting one, and the way you plotted them, you had the first 100,000 or so, and then you said there was this formula where you could get this formula explicit also when you didn't think in terms of the limit. So if you think in terms of anything related to this 100,000, do you then get a better match? Is the actual convergence process there also the same?
So I don't know exactly. I mean, we can. So the point is that when you go to the limit, then the local statistics of the zeros of the Riemann zeta function really agree with the limiting random matrix distribution. When you're not in the limit, then there's actual number theoretical information that needs to go into the 2-point correlation function for the Riemann zeros, which obviously doesn't occur in random matrix theory.
Oh, it's the other way around.
But we do. I mean, based on the work that we've been doing and sort of making the analogies, we have conjectures for how you input the arithmetic information. So the general structure comes from random matrix theory, and then you have to figure out a way to input the arithmetic separately, because that obviously doesn't come from random matrix theory. So when you're not in the limit, then you need to have a way to input basically the information about the primes, kind of separately. But always you're guided by the random matrix theory, because it always gives you the overall structure for all these formulae.
The background is statistic, and from your mystery number 1, I think the function is still Gaussian, but maybe different parameter. Or if we think that the data still in Gaussian function, but in different parameter, what happened?
So I mean, it's skewed, right? So it's not exactly a Gaussian. When you haven't gone to the infinite limit, the picture was.
This one.
Right, so it's not symmetric.
Oh, if the parameter is different, I think that's still Gaussian, but the parameter is quite not similar.
Well, I mean, it still has a mean 0, but it's a skewed distribution. So I don't think that would be Gaussian.
Thank all three students.